Hi everyone, welcome to the CSP seminar this week. So this week is our great pleasure to have our alumni, Professor Yang Liu, back to give us a talk. So Professor Yang Liu is from UC Santa Cruz, and he's assistant professor at the CS department. Professor Yang Liu received his, he did a postdoc at Harvard, and before that, he received a PhD degree from our department with Ming Yan. And his research interest is mostly in algorithm fairness and learning from semi-supervised learning and learning from dynamic and noisy data. And today, he will talk about his recent work from learning from noisy labels without knowing a noisy rate. So let's welcome the speaker.
Yeah, thank you, Tim. Yeah, thank you for having me here and for bringing me back. I'm definitely old enough to know the Michigan time, so I was just kidding with me. Yeah, and also it's not a memory. When I was a student, I was in this CSPS seminar a lot. And this topic, learning from a noise label, I was talking to Clay, was actually, I think it was back in 2013. Clay had a paper on this, and he gave a talk in the exact CSP seminar in this room. And I learned this topic the first time from this seminar. So it all started from there. Good to see you guys and Clay and everybody in this talk. My name is Yang. I'm currently a professor at CSC departments of UC Santa Cruz, and I'll be telling you something about learning from noisy labels without knowing noise rate. So I spent some time explaining what is the problem of learning from noisy labels and why we required knowing the noise rate and why it's a big issue of getting rid of this requirement. So the setting or the problem I'm trying to understand is pretty straightforward. It's machine learning 101. We have supervised learning settings. Ideally, the data comes in pairs of xi, yi. So x is a feature describing the data, yi should be the label, the supervisions. But in my case, I don't really have this nice pairs of xi, yi, but instead I'm having xi, y tilde. So I'm highlighting y tilde with a different color as well as with the tilde in front of this notation. So throughout the talk, if you see a tilde above the notation, that means it's either the noisy labels or something that is calculated using the noisy labels. So tilde associated with being noisy. Okay, so the question is straightforward. Is there a loss function that enables the learning from this noisily annotated data without the requirements or without the need of explicitly knowing the noise rate in y tilde? Okay. Again, I'm going to explain. This is often referred as the learning with noisy label question. You have a single noisy label associated with each of the data xi, no ground truths, no other things. There's a parallel literature talking about crowdsourcing. You may have multiple noisy labels associated with each data, but that's not the case here. There's only a single label, which is noisy. I'm going to spend some time telling you what are the current solutions, and there I'm going to tell you and explain to you why we need a new solution. Why we don't want this the knowledge, or we don't want requiring the knowledge of the noise rates. Okay. And primarily the talk is based on my work that was published a couple of years ago, which I call the pure loss function. This is the loss function that was having a theoretical guarantee, but without knowing this noise rate. I think it was an interesting thing to introduce. But throughout the talk, I'm going to borrow some materials from my own follow-up works, including how does this generalize to complicated noise patterns with real human noisy data, and how does this generalize to information theoretical measures? What are the implications in other learning tasks in reinforced learning, for example? So this is the plan for this talk. Okay. So noise label is pretty prevalent problem in practice. Basically, whenever you need human efforts or human annotations, human interventions to collect this data, you're going to have some noise in the data. So these are not toy examples. So both this one and this one, these are real examples we collected from Amazon Turk. So for this image task, there are 10 cats in the images, but 3 out of 10 were mislabeled as other animals. The fake news detection, which was also a highly challenging task for humans to annotate. So this reads like the Miami Dolphins are the only NFL team in the entire nation that pays property task, right? So I think this is false, but a couple annotators actually told us they believe this is true. Okay. the talk is going to focus on simple classification learnings, supervised learning task, but in many other settings, noisy label is nothing different from the reward functions in reinforcement learning. Think about these are other forms of supervisions you need for the learning task. In fairness, the noises in the data is also highly relevant to the biases in the data in a certain way. So those techniques can be applied more broadly, but I'm going to focus on the classification questions. And perhaps it was not really super surprising to us, like when you're collecting data in an uncontrolled manner, like paying people that you don't really know, you're going to see some noise. But what concerns us more is there are noisy labels even in highly controlled collection settings. So this is a really nice article published by one of my collaborators, Curtis, at MIT, that shows even ImageNet has 5% of label errors. So these are high quality, very well maintained image data sets that serve as a benchmarks for machine learning. Like a lot of the progress is, SOTA, you heard these terms, evaluations are done with this data sets, but then basically all of them are noisy. We also find noises in SafeR, which is another popular CV benchmark data set. Right, so how do we set up this? I'm going to focus on this classical learning settings, which is called empirical risk minimizations. And I'm going to mainly focus on loss function. I'm going to come back to this. But machine learning 101, hypothetically, you should have a clean set of data, xi, yi. I talked about this already. For the ease of presentation, I'm going to focus on binary classification. So you're classifying things either to +1 or -1. But all the things I'm going to talk about, they generalize to multi-class classifications. So there's no restriction on that. The goal is to find a classifier that minimize your expected prediction errors on this distribution. And many often, because you don't optimize with 0-1 loss, it's not differentiable, so on and so forth. You're going to use the calibrated loss L to make the optimization happen. You don't know the distributions, so that's why we use data. So you're going to define empirical risk using the data to approximate this expectation term to optimize with. Okay, so machine learning 101. So in our setting, clean data is not available. Instead, we have access to x and y tilde, and y tilde is noisy. And I'm going to consider the following generation model. So the generation of the noisy model y tilde in the binary case is controlled by two parameters, which I call E plus, E minus. So E plus is like when the true label is plus, what's the chance of you observing a minus label? And minus is like when the true label is minus, what's the chance of you observing plus label? Okay. So for binary case, that's how you define this noise model. I predict some questions here, so I have some slides on the next one, but give me a second. The goal is you are still trying to find the optimal classifier as if you have the clean data. So it's a really ambitious goal. You're still trying to approximate the absolute best classifier you could have when you have the clean data, but now you only have access to this noise data distribution. So that's the goal. There's a couple examples to check your understanding. This is the 2D data, so feature x1, x2. Suppose the dashed line is the ground truth discrete boundaries. Everything below should be +1, everything above is -1. But out of here, I have a 2 out of 6 that is mislabeled as -1, where it should be +1. So in this case, E plus is 1/3. So this is what the model is telling you. If you read the literature for the non-binary case, setting is often captured by transition matrix. For multi-class classification, you observe the noise labels, but then they're coming from a noise transition, multiply the hidden ground truth, the distribution of the true label. The noise transition is a matrix where the IG's entrant tells you when the true label is I, class I, what's the chance of you observing a noise label being class J? Okay. This is the matrix that is going to control the generation of the noise label. Okay. So at this point, I often receive two questions. The first question is, does this noise model capture the reality? The answer is no. Okay, so last summer, I had so many questions, I decided we're going to do a hypothesis test with real data to verify this. So we had two hypotheses to verify. The first one is human noise patterns is more complicated and shouldn't be equal to stylish noise models. This is verified. But we had a second hypothesis that is, which I refer as all models wrong, but some are useful. So the second hypothesis we had is, even though the noise model were wrong, the methods developed under this model is going to be helpful. They're going to outperform the baselines significantly. So those are the two hypotheses I had. In order to do this, what we did is we generated two new benchmark data sets for the noise labels. So CFAR is the image classification data, CFAR 10 class classification, CFAR 100 class classifications. We pushed this data to Amazon Turk and paid people to relabel them for us. So in the end, we collected a set of noisy real human annotations. And based on like how many data we collected for each image, and based on how we do the aggregations, majority vote or not, we have a set of data that has noise rate ranging from 10% to 40%. So this is great. It's not too clean or not too noisy. So perfect range for us just to study this question. So this allows us to testing that this real human noise distribution departed from the synthetic noise distribution. So they're not the same with statistical significance. Oh, that's the first thing we showed. But also we showed the solutions developed under these models outperform baselines significantly. And we actually published everything on this noiselabels.com with a companion paper appeared at iClear 2022. If I click here, first of all, we have the data loader for PyTorch. So if we want to play with this data, it should be easy to use. We have this hypothesis testing summarized here. We have the leaderboard that clearly shows, cross entropy at the baseline is only 87 for this case. But the PR loss I'm going to talk about today, well, not super encouraging, but 90% accuracy, 3% improvements. But follow-up of PR loss, CAL, is like small adaptations, and course, they can push it all the way to 95. So by doing this, by going through this practice, we're able to improve from 87 to 95. That's sort of significant improvements. Question?
Is this reported accuracy on using the noisy labels or using the ground truth?
Using the ground truth. So in this case, we do have the ground truth. Not entirely though. So I was mentioning even CFAR has some noisy labels. I just give you one example. For instance, in this one, the true label given by CFAR, the institute, was this is flatfish, which makes sense. But our worker told us it's man, which makes sense as well because it's a man holding a fish. So multiple things can happen simultaneously. I should go back to. The second question is, what's the big deal of noise labels? Is it possible deep neural nets is already robust? Is it possible, you talk about noise rate, but in the end, we train super deep neural nets, that's going to be sufficient to be, inherently robust to the noise labels. So we did this control study. Again, this is on CFAR data. X-axis shows the increase of the noise rate. We added 10% of noise labels to the training, 20%, 30% all the way. On the y-axis, I'm showing you the test accuracy of the best model trained with this data. And this is CFAR 100, this is CFAR 10. So we almost see a linear performance drop when you keep increasing the noise rate. So it is an issue. Okay. So current solutions. So this page is slightly outdated, but I'm going to focus on explaining to you what are the loss functions with strong theoretical guarantees. Nowadays, I wake up every day, essay papers on noise labels on archive. There's many heuristics that works on the training procedures. You're going to tune the architectures. You're going to tune the training steps, tune the learning rates, everything people do. But I'm going to focus on explaining to you what are the loss functions people use that give you a guarantee in the theoretical sense. There are two ways to separate this problem. The older literature or the first line of studies focus on the case when the error rates are symmetrical. So E plus E minus equals E. Okay? So this will be a homework for tonight. If this is the case, if you derive the risk of the classifier on the noise data, is actually a linear transformation of the clean accuracy on the true data. So the conclusion is this is a relatively easier case, not a big deal. So as long as the loss is symmetrical or satisfies some properties, it's going to work. You don't need additional efforts to improve the robustness. Okay? That's the good news. The trickier case is when the error rate is asymmetrical. So when E plus is not equal to E minus. Think about it, you're training a spam detection classifier. The chance of misclassify or mislabel a spam probably is different from the chance of misclassifying a real true email. So this question is trickier. And the basic idea is that first, suppose I know the noise rate. Suppose I know E plus E minus. I can use this information or I can use this knowledge to perform a correction. Okay? So I can try to define an unbiased correction of the loss function such that this L tilde, this newly defined loss, will be an unbiased estimator of the true loss. Okay. This is one example. They can do this correction on the labels, on these losses. There are various different ways of doing this. But in this example, basically this correction, this corrected loss takes the linear combination of two cases. The first one is by assuming this Y tilde is indeed the true label. So you're going to plug in Y tilde into the loss function. The second one is to take the opposite by considering the case where the noisy one is actually not the true label. And these linear coefficients are selected or balanced in a way such that when you take the expectations of this loss, it's going to be the true loss. Okay, I'm going to show you the proof. It's just two-liners. But if this is the case, you can just perform ERM with this L tilde, this corrected loss, and by law of large numbers, this is going to converge to its expectations, which is going to equal to the true loss. I'm showing this on the next slide. Suppose my true label is +1. I don't observe this. I observe a noise label. What I need to show is I take the expectations of Y tilde, this noise label, given the true label being +1, and I'm checking the expectations of L tilde, this corrected loss. But conditional on Y equals +1, there are really two cases, right? So with the error rate E plus, I'm going to observe a -1. That's how often I'm going to say wrong noisy label. With error rate 1 minus E plus, this is the case I got it. My noise label is actually correct. Okay. And then I just write this into the two cases, plugging the +1 and -1 respectively into the corrected loss function. And the rest is to plug in this definition of the loss function. Things just canceled. You do the algebra, it's going to be equal to exactly the loss function invalidated as +1, which was your true label. I think the coefficients were back engineered in this way. You want this to be unbiased, and then you identify the parameters, but that's how they do the proof. It's pretty straightforward. But now this is going to help you prove this summation is going to converge to the true losses, even though you don't really know the true losses. This is a really neat idea. I've been applying this approach in my previous research, but it has some caveats. First of all, approach requires specification error rate E plus E minus. And then many often the estimation procedure require either you have some ground truth to tune the parameters or to estimate the parameters, or like what I did before, I required multiple noisy label to sort of define a tensor and using the tensor information to identify the true parameters of the hidden graphic models. That's a long story. And many times when I work with industrial partners, they don't really have this data to support this estimation in the first place, not to mention to apply this loss function. Thirdly, even though you can estimate, what I observe is that the noisy copies of E plus E minus often becomes the bottlenecks of learning. Right? If we don't estimate the parameters accurately, this is going to introduce another layer errors. Binary is okay, E plus E minus, 2 parameters, not big deal. But for K-class classification, that will be K-square number of parameters to estimate. That will be even less stable. Okay. So for some time, I've been hoping to find a function that can do this correction, but without using the noise rate. This is what I call a pure loss function. This loss function, just a really quick highlights before I give you the mathematics. This is a function that's defined across multiple samples. Okay. So when I'm trying to evaluate the losses of one sample, I'm going to randomly pair a pure sample to help my classifier punish over-agreements with the noise labels. I'm going to give you details. No need for noise rate, and there's basically no need for changing the existing loss functions. All I need to do is to reshuffle the data at the very beginning and put 2 sets of data into the trainings And each set of data goes through a loss function and I take the difference. Okay, this is on next page. Here it is. So pure loss has a following form. The first row is the data, is xi, the features. Second row is noise labels. And each of the column is one data point. For each sample xi, y tilde. So I'm trying to evaluate this pair xi, y tilde. Before I take the loss, I'm going to randomly draw two other samples, P1, P2. So P1, P2 are entirely randomly selected from the rest of the database, no correlation at all. And I'm dropping y P1 tilde. Okay, drop the label with the first data. I'm dropping xp2 from the second pair. And I'm pairing xp1 with yp2 tilde. So this is what I call peer sample. I'm drawing from the rest of the peers, mismatch. And now pure loss take the following form. Keep your original evaluation. This is the loss function you define on xi, y tilde, like people often do. But I'm subtracting the loss function of how classifier predicts xp1 with respect to yp2 tilde. So this is the mismatching part. So I'm letting the classifier to predict on xp1, but I'm evaluating on yp2 tilde. So you might be wondering like why the classifier should be predicting anything accurately on this one. That's exactly the reason it shouldn't be. So if the classifier actually indeed predicts accurately on P1 with respect to P2, that's a signal to me the classifier is overfitting, or the classifier is being coordinated by the noise pattern in the data. So this is serving as a punishment term. Okay. That's why I'm subtracting the second loss term from the definition. And each of the baseline L here can be any loss that people use, cross entropy, hinge loss, or whatever. So the only thing to do is add this additional term. I'll give you 5 seconds. Sure.
Yeah. So why then do you need like one randomly sample data for each data sample? You can do like ratio 1:2, like 1:10.
Right.
Any combination.
Right. Yeah, that's a good point. So this is original construction. So Lei's question is, why do I need to do this shuffling every time? I can just compute the distribution and then multiply the parameters in from the losses of this yp2 tilde. That's another way to implement. It will be relatively more stable. But I think this way is probably easier to illustrate this whole thing. But this is on next page. So I'll give you explanations why this works. Basically, when you take the expectation of the pure loss, it calibrates the following terms. The first term is the same as the typical loss function does. It tells you the classifier should be fit to the data, right? You should be fitting the data. And the first term is telling you, okay, I'm trying to reward the classifier if the classifier agrees, the prediction agrees with the noisy label. That's what it does. But the second term is what I call a punishment distribution. It tells the classifier you shouldn't be predicting too accurately on a randomly selected noisy label from the rest of the distribution. In other words, this is capturing the marginal correlation or the marginal agreements between these two random variables, this classifier and then this noisy label y. Because think about you're tossing two coins, right? Even though the two coins are entirely irrelevant, they have a certain chance of agreeing. But that does not mean you design the coins to be agreeing with each other, right? So you toss a coin 50-50, toss another one 50-50, they have 25% of agreeing. So this is second term that is capturing hypothetically, even though the classifier and noisy labels are entirely independent, they still have a minimum chance of agreeing. So this is what this term is capturing. And now the loss function is telling people to find the classifier to maximize the marginal improvements in terms of agreement. Okay, give you an example. Suppose these are five data points I had. The first row is the classifier's predictions, is all plus. The second row is the noisy label prediction, is also all plus. This is the ideal case if you use cross entropy, because cross entropy finds out this is great. Classifier memorize all the data, zero loss. Okay, this is the best case you can hope for. Now, if you check in pure loss, this is what happens. Sure, for any pair of this data, you always agree. But then if you randomly take another two, they also agree. So 1 - 1 is 0. So this is telling the classifier you're not really memorizing more information other than just like randomly taking a guess based on the noise label distribution. And this I tend to think about this as capturing the marginal agreements, and it has a deep connection. But only after this paper I realized it has a deep connection to information theory, which I'm going to explain shortly. But this notion has appeared in the crowdsourcing literature, which is called the correlated agreements. You're trying to check the agreements between two information sources, but only in a correlated way. The second explanation we find is this loss function is really asking the classifier to be confident in the predictions. So this is the controlled experiments we did. Again, really simple 2D classifications. The inner circle is class +1. The outer loop is the class -1. So 2D classification. This is a clean case. It's a relatively easy classification. We train a 2-layer neural nets with cross entropy. This is the descent boundary, which achieves 100% accuracy. It separates this inner from outer really nicely. But if you plug in the noise labels, on the left-hand side, we added 20% noise labels to the training. On the right-hand side, we added 40% to the trainings. You can see like some of the blues are flipped to red, some of the red are flipped to blue. So one of the reasons the noise labels are hurting the performance is because the existence of noise labels creates really confusing patterns for the classifier to memorize. Right? So in this region, there are like 5 blue points, but 2 red points. Right? When the classifier is trying to look at this region, it got really confused. So as the outcome, the decision boundaries got really blurred. It's not as sharp as before because they don't really have a high certainty about which class to predict. So these different color bands represents the prediction confidence in each of the regions. So 20% is okay-ish, but 40% the decision boundary got destroyed entirely. There's nothing really to predict in this case.
What loss function are you used in training?
Cross entropy. Good question. But
quick question.
Hmm?
So even though your blue and red points moved, what is the reason that you continue to have this kind of space of unoccupied?
oh, this outer space unoccupied things.
So no. And just basically, if I look at the geometry, right, the location of these points, there is kind of this space in between the inner cluster and the.
Yeah. So I'm not changing. I'm not adding. So for a controlled study, I'm not adding new points. I'm only flipping the colors of the existing data points.
And there you limit. Oh, I see. You're not changing. Yeah.
Yeah. So the color represents the label.
You're
Right.
changing the label. Yes.
Yeah. Features are X1,
Yeah.
X2, but colors are the labels. Sorry, I should explain that. But this is pure loss. 20% versus 40%. So one thing you can notice, still pure loss missed some points here, but the discrete boundary got really sharp. So the loss function tells the classifier, if in this local region, if you realize like one direction might be the correct directions, try to predict confidently on this direction. So this does change the dynamics of the training. So this is one thing what we observe. And as the afterthought in 2021, we had a paper that officially proved this. For a pattern X that appears sufficiently enough in the training data, this is the informal statements, but you can think about there's a similar pattern to cat that appears in different images and that appears sufficiently in the training data. Then with high probability, training with pure loss is going to give you a classifier that always predicts one label with confidence 1 or with confidence 100%. That's what is observed in the empirical experiments. Even though, yeah, question.
Why would you want it to be super confident?
Because you want to escape from this mixing pattern that is due to the existence of noisy labels. I agree with you. If the data is clean, there's a debate about do you want to be confident or do you want to be more generalizable? But in this case, I think the region is less confident because of the mixing patterns of noisy label and true label, and you want to be confident in this case. But one caveat though, the discrete boundary is not as regular as before. I think this is the artifacts of pure loss being non-convex. This is just something I'm going to explain shortly. So this is not a convex function by default. Okay. So this was the first theorem that was really encouraging. For some moments, for some time, I was trying to prove, this is a mission impossible. You cannot find a loss function that is not really depending on the noise rate, but at the same time give you a theoretical guarantee. But this is the first result that was super encouraging. That shows pure loss is actually invariant to label noise. And the result is pretty simple. This is saying, when I take the expectations of pure loss over the noisy distribution, x multiplied y tilde, it's almost the same as if you're taking the expectation over the clean data distribution of pure loss. And every dependency of the noise rate is subsumed in a constant. So E plus E minus are in front of this expectation term. And this tells you if you are minimizing on the left-hand side, it's the same as minimizing on the right-hand side, which you don't have access to. Question.
What does it mean to use pure loss on clean distribution?
That's a good question. That's on the next slide. Okay, so this is telling me, first step, if you're gonna apply pure loss, clean, noisy does not matter. Okay? So you are looking basically at a loss function as if you have the clean data. But now the question is, do you modify the loss too much such that it lost information on the clean distribution? That's a really good question. Again, for simplicities, I'm going to plug in, just for demonstration and the ease of the proof, I'm going to plug in 0, 1 loss in 2 losses. So remember, there was L in both terms. It can be arbitrary loss, but I'm going to plug in 0, 1 loss. Okay, and as a consequence, I'm going to call this 0, 1 pure loss. I'm defining this H tilde star as the optimal classifier I can get for minimizing the noisy label distribution of 0, 1 pure loss. And the first proof is that when the data is balanced, so this P is the population of the plus labels. So if it's entirely balanced settings, plus label is the same amount as minus label, 50-50. Then this noisy optimal classifier you train on pure loss is going to be exactly the optimal classifier as if you train on the clean distribution. Okay, so here, there's no peer. This is the clean expectations over 0, 1 loss. So how do you prove this?
There's a question from the chat.
Sure.
Does the pure loss theorem apply to multi-class case?
It does. So pure loss does, as I said at the beginning, does apply. So in the paper, we do show it generalized to multi-class classification. Again, you random sample data, mismatch them into the loss function. So theory is generalized too.
Thanks.
So I'm wondering, like for imbalanced case, especially when the data are very imbalanced, will this pure loss make the training like converge very slowly?
That's a good question. Yeah, in 2 slides, I'm going to talk about the imbalance case.
Thank you.
The proof was actually surprisingly simple. Basically, you take the expectations, probability 1 over 1. You have 2 terms, it's additive. So each of the term is becoming probabilities, expectation over 0, 1 indicator functions. And this is nothing different. This is checking the classifier's prediction error on the noise data. But the second, because you mismatched, they're entirely independent. So you're only having 2 cases. When classifier says it's -1 and noise label says it's +1. And because of the construction, they're entirely independent. So this term is become the multiplications of 2 independent probabilities. And there's a second case, the classifier predicts +1 and the noise label predicts -1. That's all I need to do. Step 2, each of these terms involving noise label y tilde can be written as a functions of the true priors and the noise rate. For instance, when do you have a noise label being -1? This is conditional on the true label being -1, and you got it correctly. And then true label is +1, you got it wrongly. Okay. And step 3, plug them all back into this first equation, rearrange terms. You prove this theorem I had at the very beginning. And step 4, when you have balanced equation, you're going to check this one is nothing different from the true clean risk on the 0, 1 loss, plus minus a constant. Okay. So putting up everything together, you showed the noisy expectation of pure loss is going to be an undefined transformation of the true clean loss. which is going to return you the same minimizer. So what if data is imbalanced? What if the prior is not equal to half? It turns out there's a really simple way to unify these two cases, which is just by punishing less. Okay, so I'm going to introduce a quantity alpha, which is a scalar, in front of the second pure terms. The basic idea is like, I thought if the data is imbalanced, I should be punishing in a slightly different ways. And turns out this is a bit overclaiming, which I admit. In this case, the optimal alpha does depend on the noise rate. So if you want to find the optimal alpha in order to balance the punishment and the training, it has to know some information about the noise, at least the summation of E plus E minus. So this is the caveat of this results for the imbalanced data.
Can you remind me where is p equals 1/2 used in the previous?
Right. So where's the p equals to 1/2? It's from step 3 to step 4. So when p equals 1/2, this pure loss on the clean data is going to be equal to clean loss on the true data. The 0, 1 loss on the true data minus a constant. So this is where I use the p equals 1, p equals 1/2. But this is a good generalization. So this delta captures the imbalance of the data for the clean and noisy case. When the data is imbalanced, this term is 0. So alpha equals 1, that recovers the pure loss I told you earlier. But also when the noise is 0, so people wonder what happens if the data is actually clean. There's nothing to concern about. In this case, E plus E minus equals 0. These two equal the same, and then alpha becomes 0. So meaning if the data is really clean, you should kill the second term. Just do the same 0, 1 loss. So this is I think this is even though it has its caveats of dependency, I thought it's really interesting unifications of all these cases. In practice, we can tune the alpha with noisy validation data. Basically, if you see the noise rate is high, give a larger alpha. When the noise rate is low, give a smaller alpha, and works pretty well in practice. And I talk about 0, 1, but in the papers and follow-ups, definitely we don't want to optimize 0, 1. You can plug in any differentiable loss functions, replace them with 0, 1, and we can prove similar stuff in terms of this arbitrary L enabled pure loss is going to be classification calibrated, meaning as long as you are converging in this L space, your classifier's errors is also converging on the 0, 1 loss space. So this is the definition of classification calibration. We have some conditions, but I'm going to skip them. It does not hold as always, but these two cases are pretty general, even though the second case requires the baseline loss function is the second order derivative is constant, which is not the case for cross entropy, for example. Cross entropy, take the second order derivative, it's not a constant. But I want to show some empirical results, but I already showed you the website, so I'm going to skip this part. If you're interested in the performance of these loss functions on the noise data, take a look at noisylabels.com. We're continuing to update the leaderboards and everything. There's only one figure I want to show you that shows pure loss and its follow-ups are able to escape from this local minima, which is like when the classifier is overfitting to the noisy labels. So this one shows you the training dynamics of a deep neural nets. These are x-axis are showing the epochs. The blue figure are showing you the training accuracy on the noisy label distribution. So this is not the true training accuracy. This is calculated on the noisy using the noisy training data. The orange one is also calculated using the noisy validation data. So not surprisingly, these two they're pretty aligned with each other. And you're going to notice if you're going to just do cross entropy using these measures, noisy validation, noisy data, you pretty much want to stop here, right? You hit the maximum accuracy, and that's where you say, okay, my accuracy start to drop. That's my best epoch. I'm going to take this model. But pure loss does not stop here. So pure loss continues to trend, even though these two noisy quantities are dropping, the clean validation continues to improve. So this is the training dynamics of pure loss. So it was able to escape from this overfitting phenomenon.
What's the benefit of having to select alpha versus having to choose the ratio of errors?
Oh, yeah. So what's the benefits of tuning the alpha? So first of all, the complexity of tuning the alpha is much less because it's a single scalar as versus to the noise rate is often a matrix. Okay. And I skip the details, but in the real operation, you often need to take the inverse of the matrix, which give you another amplifications of the or reinforcements of the errors in the training. But this alpha is additive and it's a single variable to tune with. With the remaining time, I want to tell you one connection. Again, we didn't know when I should know, but then wasn't entirely clear until 1 year later of this paper. That is perhaps it's not as novel or not as surprising as I was thinking. It actually connects deeply to a measure in information theory, which is called the F divergence. Okay, so the story is this. We talk about pure loss being a punishment or as a regularizers in the training. It has two terms. First, a joining distribution, second, punishment distribution. Let me denote this as P and a Q. Okay. So the question I had is like, can I find a different way to punish the classifier instead of just doing these additive things? The first thing I tried is to unify or rewrite this equation by writing this as expectations of P over a function G. So in the pure loss case, G function is the indicator functions. Expectation of indicator becomes the probabilities. The second one is the same story, expectations over Q of a G prime function. So I intentionally kept G prime to be different from G. So I was hoping to say if there's a possibility to, again, create an asymmetry in these two functions, so I can be punishing in a different scale. So G prime can be different from G. So we tried different combinations of G prime and G, and there's one combination that looks really familiar to us. Which is by replacing G prime with a convex conjugate F star over the first G. Okay, so I haven't tell you the details of F star. What is F star? But think about this is just a convex conjugate function of something. But then the G is the same as the first term. Okay, so I'm choosing a particular G prime in my second term as a punishment. And if you have taken information theory here, I believe it's 555. That's a course number. 550. Sorry. I failed the class. But if you're taking information theory, this is exactly the variational form of the F divergence defined over these two distributions, capturing the differences between the two distributions. And pure loss is just like one very special way of checking the difference between these two distributions. And we proceed to prove something that is really, I think, new to the information theory literature and also very similar to pure loss. So if I define this variational difference or the variational form over the noisy label distribution, so I'm using the tilde VD to denote this noisy calculation of this variational form, we are able to prove this. So the noisy version of the variational difference for any F divergence function equals to almost the same linear transformation of pure loss. It equals to noise rate multiplied the claim, the true variational difference, plus a bias term. This bias term depends on your choice of the F functions, depends on the choice of the classifier you're looking at. But pure loss corresponds to the case where the bias term is 0. Okay, that give you the linear transformation property we showed earlier. But not only pure loss. Total variation distance, which has a really similar form as pure loss, has a bias term being constant. Okay, so a bias term being constant is also good enough. Right? You're again having an affine transformation. Your noisy measure you can calculate is the affine transformation of the true variational difference term. Then you can do your optimizations of the noisy variational difference term. But not only so. For many others, like Jensen Shannon's and KL, even though the bias term is not a constant, it's at a higher order. So we are able to show the bias terms are at the order of e1 minus e plus 1 minus to the square. So compared to the first term, it becomes negligible. It does not affect your optimization as much as it should be. After all this, we are able to claim maximizing the F divergence is actually robust to label noise for a broader set of F divergence functions. And then based on the F divergence literature, we are able to create new loss functions to make the training robust. This is a list. We checked both theoretically and empirically. Total variation checked. Jensen, Shannon, KL, Pearson, Jeffrey. These are good ones. Reverse KL that is not robust. It failed the test. The last one is squared Hellinger. That one also failed the test. So there are some F divergences are not as robust as the others. Okay. Okay, these are the empirical results. I think it's not important at this moment. Skipping this one. I'm concluding my talk by mentioning something that hasn't been settled. So we talk about the loss functions that requires the noise rate. That one worked. Okay. With the estimation of the noise rate, and we talk about pure loss. Now we don't really require the noise rate anymore. So it's estimation free. You are doing a startup today. You give me the problem. We plug in the loss, ready to go. But what are the remaining questions? So one thing I found to be interesting is to looking at the performance at the instance level instead of population level. So most of the analysis, including both theoretical analysis and empirical analysis, they look at these quantities, expectations over an entire distributions of the loss functions and the performance of the classifier. But how do these solutions or how do the noise labels affect each individual subpopulation of the data? Okay. Say like you improve your classifier from 80% to 85%. Okay. Is that you're improving this from 80% to 85 for every single region of the class of the data distribution? Or is it possible you're improving one part of data from 80% to 90%, but then the other part of data actually dropped from 80% to 75%, in which case it will be a concern because you're promising people, you give me a new loss functions that they're gonna do me good, but then it's actually hurting subset of data while improving the rest of the set of data. We do observe there's a strong massive effects in these settings, meaning many of the methods we are doing, they are making the rich group, the better performing group richer, but the poor group actually gets poorer. Okay. Let me explain this. This is a figure I drew. Basically, we showed if the data has a long tail distribution, it has a really fat tail. So I'm ordering the data based on the frequencies. You can think about on the left-hand side, these are the patterns with high frequency. They appear a lot in the data. On the right-hand side, these are the rare data. They don't really appear much, but there are many of these long tail data. Okay. What we show, for sure, for high frequency data, its influence or its impact is higher because this data is just going to be observed more in the test. So you should care about this data, but they are actually easier to fix. So many of the solutions, including pure loss, is able to fix the errors on this data very easily. But the long tail distributions, they don't really happen often. Their impact is smaller, but they're harder to fix. Many approaches, including pure loss, are going to fail at this long tail regime. So
I have a related question, which is, so you said, I know you said your noise model may not be realistic, but the method you develop can still be useful.
Right.
I have a question on the noise model. The most distinct thing here is it's independent of the feature.
Right, exactly.
But you have done human subject studies. What do you see? Are noises actually dependent on features?
Right. So the noises are definitely dependent on the features. There are two observations of the dependency. The first one is that dependency depends on how far away the data is from the discrete boundary. Okay. If it's close to discrete boundaries, meaning that's a harder example to classify with, you're gonna see more noise in this data. That's the first observation. The second observation is errors, they do happen in clusters. if one people make one error on one data, you're gonna see similar errors on similar data, right? So many often we see there's one cat that was one breed of the cat was misrecognized by one people. You're gonna see similar errors in other people's annotation of similar cats of this breed. Okay? So these are two most important things. But the third one, I don't have a theory, but there's a hypothesis. The error should also be depending on the on where the data is at the spectrum. So the long tail data are especially vulnerable to annotation errors because they are like outliers. People don't really observe this data as often as others. So a lot of mistakes on the long tail. Some of the works I do with me, and so very naturally people ask the question, can this be fixed easily? Because there's a relevant literature called fairness in classification, right? You're trying to minimize the classification accuracy, but at the same time, you're gonna give constraints. You're telling people your classifier has to be equally accurate at different parts of this data. Okay? So in this case, this F is a fairness measure. You can think about this just accuracies, and Z defines your group, like which group of the data you should be looking at. And then this constraint is just saying, a classifier should be equally the same in terms of these measures. But it turns out that this is not an easy question either, because if you're going to do empirical risk minimizations, we talk about fixing the loss functions, but we haven't talked about fixing the constraints. Right now, you're only having the noise labels to calculate the constraints. They're going to give you trouble. For instance, this is real experiments we did on adult data. So this is predicting the income levels of the people. So each of the data is the person's profile. We are trying to predict, if this person's income is higher than some values or not. Binary classifications. We break the data into male and female. And then what we observe is, if you look at this, I think we added noise to one group. We added noise to the male group. So we added label noise to male group. We keep the female group clean. This is a baseline classifier. We do nothing. We just train the classifier. We observe some unfairness. If you look at the last row, the female group has a 91% accuracy, while the males only have 80% accuracy. So there's disparities in the performance. But now I'm training a fair classifier, claimed to be fair classifier, but constraints are defined with respect to the noise label. The outcome is as follows. Both groups' accuracy actually dropped. And this difference is actually reinforced. Now, for the female, it's 88% accuracy by adding these fairness constraints, and the male group dropped to 72% accuracy. So not only both groups' accuracy dropped because of the existence of noisy labels, the gap is also reinforced. Okay? So that is to say, if you have a noisy label settings, especially you have some noise on one group, some other noise on the other group, adding the constraints or imposing the constraints is not as easy as people were thinking or suggesting. Okay? So this is the observation we have. Yeah, I think that's the last slide. I think this is the concern, but also this is the opportunity. Yeah, this is something that might worth the explorations and your research efforts. Very interesting in this. All right. Thank you all.
Thanks, Jan, for a great talk. Any questions for the speaker?
If there's any question, please.
Actually, I have two questions.
Sure.
So the first one is like for the last issue you mentioned. One reason I'm thinking is because maybe you have a lot of data for group one, not so many data for group two.
Right.
But when you add the penalty, it's kind of also proportional to the size of the group.
Right.
And you just modify that, say, for label one, I have 50% penalty. For label my next one, also 50% penalty. So equalize.
Oh, I see.
Can that help alleviate the issue?
That's a good suggestion. So the suggestion is, because I know the groups are imbalanced and possibly the noise rate are imbalanced, I'm going to reweight one group when I'm calculating this measure and then trying to be equalized.
Right.
Yeah, so the paper, we had a reweighting procedure to remove this issue down here at FACT, this fairness conference. Yes, so you can tune the weights properly to do this, but the optimal ways to exactly remove the gap, again, depends on the noise rate.
Right.
So it's not super easy to tune, but you're right. So by balancing these measures is going to help you fix this one.
My second question is, when you define the loss function right here, you randomly sample 2 data points and you kind of combine them. Instead of combine them, can I just randomly generate Y? Will that be the same?
Yeah.
Why I need to take,
Yeah, so that's the question I think briefly discussed. So instead of randomly sampling noisy Y, I can just like first calculate the posterior of the Y from the data.
I just randomly pick Y.
Oh, you cannot
Completely random.
you cannot completely randomly pick the Y. So your random pick has to be in proportion to the noisy label distribution.
Okay.
So if noisy label is like 80% plus 1, 20% minus 1, you need to do this random pick by 80% to 20%. You cannot do 50-50.
What happens if I do 50-50? Like,
If you do 50-50, first of all, you don't have the guarantee.
Okay.
You don't have the linear properties there. Secondly, I think you'll be over punishing one class in some ways. Right? You want the punishment to be respecting the noise rate in the data, which is encoded by the noisy posterior.
so if they are symmetric, then maybe it's fine. But if
It's entirely symmetric, that will be fine. Yeah, the other way people do, again, they don't have a theoretical guarantee. After this paper, the other way people do is also similar to contrastive learning. They don't randomly pick a label, they pick the label that is most likely to be wrong. And then they punish with respect to the wrong label. Again, that's another story.
Thanks.
Great. Thank you all. Again, my email is youngliu@UCSC, full name spelling. Feel free to reach out if you have questions later.
I have a question regarding one of the theoretical results.
Sure.
So I know. First of all, it was a nice talk. Thank you. And my question is, I noticed there is a term which is 1 minus e plus 1 and e minus 1, which is a summation of the error rates for the 2 classes.
Right.
So I'm wondering, what is the corresponding term when we have multiple classes? Would it be 1 minus like E1, E2, etc., all the way to some EK?
Yeah. So
Yes.
if you have multiple classes, this is going to be 1 minus the summation over the error rates across different classes. Yes.
Okay. Does that mean we need to have more stringent conditions for multi-class so that the error rate won't, the sum of the error rates cannot go beyond 1?
Right. The summation of the error rates cannot go beyond 1. That's true. But I believe the error rates will be corresponding to E divided by K minus 1 if K is the number of classes.
Oh, I see. Thank you.
Yeah, so this is minusing the per class noise rate. It's not the entire noise rate.
I see.
Cool. Yeah, that's a great question. Yeah, that's a nitty-gritty detail. I thought, I don't need to mention, but that's a good catch.
Can I ask a question from Zoom?
Yes, please.
Yeah, I have a question regarding the there was like a one figure that you show the training accuracy on the clean label data set and the training accuracy on the noisy and the validation on the noisy label. There was like a figure that you showed before, and I recognize that there's the same pattern for the training accuracy on the noisy label data and the training accuracy on the validation with noisy label.
Oh.
Yeah. My question is that why the pattern is the same? Because like, for example, human being can make mistakes, follow a certain rule. Like for example, on one image I made this mistake, and when I saw a new image, I might make the same mistake. But it's not necessary. Yes, it's not necessary like the noisy validation accuracy. Yeah, the training accuracy is called the same pattern as noisy validation accuracy.
Yeah, the volume is relatively small, so I don't fully capture the question. But if you're referring to this figure, so first of all, this figure is generated on a synthetic data. So this is the synthetic noisy labels generated by flipping. So this is not the real human noise labels. That's the first thing. And I don't capture a second question. Are you asking like why this training accuracy and the noisy validation accuracy, they're really similar? If that was your question.
Yeah, that's the question.
Yeah, so that one to me, that was not really surprising because these two are basically, so first of all, we are not tuning any parameters. So we are looking at a single model. And because the noisy training data and the noisy validation, they are generated, they are synthesized under same distributions. So they're roughly in the same distribution. And now you're calculating the measures, they're basically aligning with each other. But again, this is because the data is entirely synthesizing. So
yeah, so let's think about like a model that is power enough to overfitting exactly so to those noisy label data. Let's say like the instead of the decision boundaries, instead of like as smooth as you showed before, it's like actually extremely narrow and follow like there's a small circle near those noisy labeled examples. And in those cases, when you see a new noisy example, it does not necessarily to make those mistakes.
Right.
If the model during the training is already overfitting, it's like extremely powerful and overfitting to those training labels. And that, if that's the case, then a noisy validation accuracy won't necessarily look like this.
Right. I agree with you. I agree with you on that. I think practically they don't go along entirely in the same pace. There may be some mismatch between the training noisy accuracy and validation noisy accuracy. But again, part of the reason is like for each of the training and the validation, we have a lot of data points. And for each of the data points, we are generating the noise labels in the same way. So you're gonna have some miss and catch, but then overall on average, they are converging to similar numbers. That's my guess.
Okay,
but that's a great question.
Thank you for the very great talk.
Thank you. Yeah, so I forgot to mention, I think Sheng, he was in the audience. They also had a really nice paper that does not focus on the loss function, but focus on the training dynamics. You know, there's a lot of other things you can do to improve the robustness. But today, this talk, I don't want to give you the impression this is the only thing people do. This is only focusing on the loss functions.
Thank you, Professor Liu, for the nice introduction. Thank you.
If not, let's select the speaker again.
Okay, thank you. Thank you, Qing, for hosting the talk.
Yes, yeah.
Huh? Right.
This second term is regularization.
It's a regularizer. 对，其实我后来发现它其实有点像一个 confidence regularizer，就后面是它不是 convex， 对对对。但是它们两个叠加在一起，它是一个 convex 减 convex， 所以有的时候会是 convex。对对对。啊，感谢。
我有一个人想
啊，
那个多少是
可以是负的，
可以就正常来讲，
每个人关于负的，就是说你需要比的是说你好的 model loss 要比另外一个小，它到底多负没关系的，你是负的，我们实验中你要不想要负 loss， 你加一个 cost， 加个100上去，每个点都加100，它就变成正的。
OK，
这个其实关系不大，
但是没有那种 minimize， 就比如说负的话，就没有 minimize 这个，就如果有负的那我，
但它是有下限的，它不是可以 arbitrary， 所以对，所以还是一个 minimization。
OK 了，就越不好的情况下，可能
它越
对。
对，我刚才跟那个殷老师聊了，我们和老师聊一下那个 reference， 所以tomorrow，
so I can make the meeting.
Oh,
yeah， 感觉非常有趣，有机会可以
商量一下。
好的。你能带我去一下你们 lab 吗
I'm be driving.
Okay.
But like I meant the spectrometry.
So you can overdo it.
Yeah, because I'll be driving like in the afternoon, and that's when the tomorrow's meeting. But so which meeting were you talking about?
Spectrum meeting.
Yeah, that's the one.
So, Qing, do you know how to close this one?
Oh, yeah, I need to close it. Last time we close it and